444 subsequence reconstruction. So for this kind of a problem, normally I think we're gonna call it a construct problem. If it is a construction problem, normally we need to construct it and then we're gonna find a solution. I mean, if you just read the problem, maybe you cannot solve it. So why not just make a drawing to solve the problem? Yeah. So first, let's try to understand what it is. Yeah. So we are giving an integer array nums of less n, and nums is a permutation of integers in the range 1 to n. So definitely, if this n equals to 3, it means we have 3 numbers. It is a permutation of 3 numbers. Maybe we're gonna have a sequence of 1, 2, 3. So this is the definition of the nums. And we want to check if nums is the shortest possible and the only supersequence. Yeah, we should understand what is the supersequence. It is the opposite of subsequence. So the shortest supersequence is a sequence with the shortest length and has all sequences I as subsequences. So let's try to understand the first example. So for the subsequences, we have 1, 2, and another subsequence we have 1, 3. So for 1, 2, 3, definitely it is a supersequence, because if we delete 2, we have 1, 3. If we delete 3, we have 1, 2. So we have those 2 subsequences. It is okay. Yeah. Now let's just continue. So there could be multiple valid supersequences for the given array sequences. Yes, it is. So for 1, 2, and 1, 3, it might be multiple supersequences. It might be 1, 2, 3, or it might be 1, 3, 2, because this is also okay. So there might be multiple valid supersequences. Yeah. So for example, we are using this example 1, 2, 1, 3. So this is okay. This is my example. So it is okay. While for sequences 1, 2, 1, 3, 1, 2, 3, so the only solid supersequence possible is 1, 2, 3. Yeah, because if we have 1, 2, and 1, 3, but we also have 1, 2, 3, so definitely it's gonna only be 1, 2, 3. Because if it is 1, 3, 2, it is not possible because they are not the same. Because 1, 3, 2 and 1, 2, 3, they are not the same. Definitely, it is not possible. Because 1, 3, 2 is not a subsequence of 1, 2, 3, but 1, 2, 3 is a subsequence of 1, 2, 3. So this means 1, 2, 3 is the only supersequence. But 1, 2, 3, 4 is a possible supersequence, but not the shortest. So this is also obvious. Yeah. So we're gonna return true if nums is the only shortest supersequence. We're gonna only need to find 1, not 2. If it is 2, it means it is not possible. Yeah. Or false otherwise. If it is a 2, it is a false. So for example, if we find a supersequence might be 1, 2, 3, 4, so it is not the supersequence, because for this example, yeah, it is 1, 2, 3. Or might we find a supersequence of 1, 2? Of course, this is gonna be false, because 1, 3, it is not a supersequence of 1, 3. It is not a supersequence of 1, 2, 3. Yeah. So here is the definition of the subsequence is a sequence that can be derived from another sequence by deleting. So this is why I deleting some or no elements without changing the order. So the order is important of the remaining elements. Yeah. So if we basically understand the problem, so it means at least we can try to solve it. Yeah, because if you didn't understand it, definitely you don't know how to solve it. Yeah. Now the second step is that we're gonna try some examples, because currently we have no patterns. Maybe we're gonna try to check some examples. Maybe we can find a pattern. If we can find this kind of a pattern, definitely we can solve the problem. Yeah. I mean, if we have the background knowledge with the pattern, we can solve the problem. Yeah. So let's just try to check the first example again. So for 1, 2, this time we're gonna make a connection because there's a sequence. So we're gonna make a connection. 1 ported to 2 and 1 ported to 3. So this is the first example. So this is a false. Yeah, because we have 1, 2, 3 and 1, 3, 2. There are 2 supersequences, but we only need 1. So this is why it is a false. Yeah, and let's try to check the second example. The second example, we have a sequence of 1, 2, 1 ported to 2, but our nums is 1, 2, 3. Yeah, but for the supersequence, 1, 2 is enough. We don't need to have 1, 2, 3 because it is longer. Yeah, so this is also a false. Now let's try to check the third example. So we have one pointed to 2, one directed to 2, and another one directed to 3. So this is a 3, and 2 also directed to 3. Now we are going to find some pattern. So for this one, there's only one supersequence. It is 1, 2, 3, and we find it is only 1. So we're gonna return true. But why it is only 1? So we're gonna find some pattern why it is only 1. So first of all, let's just check this number 1. Yeah. So for this number 1, it is here. So for let me use another color. Maybe it's better. Let me use maybe maybe red. Yeah. So for this number 1, we are starting from this number 1. As you can see, we are having this 1, 2, and 1, 3. So we are starting at this number 1. And for the next step, what are we gonna do? So we have two choices. One choice is 2. Another choice is 3 directly. But can we choose 3 directly? We cannot. Yeah, if we choose 3, 1, 3, definitely it is not the right answer. Yeah, it means we cannot choose 3. But why we cannot choose 3? If you check the structure, it is a topological structure because there's still other connections with 3. It means we cannot choose 3 directly. But for 2, there's only one direction. It is connected with 1. So it means for the next step, we're gonna choose this 2. Yeah. And now for the third step, we're gonna choose 3 because here we have no connections. And then we're gonna choose this number 3. If we can choose like this 1, 2, 3, and we can get the result 1, 2, 3. If this is equal to the nums, definitely this is the answer. But why we can find this kind of answer? This is a topological sort. Normally, if there's a sequence, it is a topological sort. And for this problem, this is also topological sort. Let's try to find the topological sort. Yeah. Now we are going to use the topological sort to solve the problem. Currently, we are starting at this node 1. It is okay. We have this node 1 inside the queue, and we can get the result. Now, we're going to use the topological sort to get this node 2. Because for this node 3, it connected with 2 nodes. It is not yet. So we're going to get this node 2. Yeah. Now, the second step, we're going to get this node 2. And now, for these connections, the integrate of 3 is going to minus 1. And because this node 1 has already tapped, it is also minus 1. And for this node 3, the integrate is 0. It means for the next step, we're going to get this node 3. And there's only one sequence, that is 1, 2, 3. And this sequence equal to nums 1, 2, 3. And we're going to return true because we find a sequence. So by using the topological sort, we can only find one possible result. So we're going to check this result with other nums. If it is equal, we're going to return true. If it is not, we're going to return false. So in this example, we have the node 1, but it is connected with 2 nodes. It means for the next step, we have 2 choices. There are too many nodes. Because there are 2 possible ways, definitely it's going to be wrong. So in this way, we're going to check. If there are too many ways, more than one, definitely it's going to be false. If there's only one case for each of the BFS, each of the topological sort, so definitely we're going to get the answer. If this answer equal to the result, definitely we're going to return true. If it is not, we're going to return false. So currently, if you understand it like this, basically, you can try to use the topological sort to solve the problem. So for me, I'm going to use the BFS. So I'm going to prepare a graph and integrate. So the graph is going to be default dict, and inside is going to be list, and the integrate is going to be an empty array. I'm going to prepare 0 times the length of the nums plus 1. Because for this time, our graph with all the nodes is just starting from 1 to n. It is not from 0 to n, as you can see from that. So it is 1 to n. So this means that while we are preparing for the adjacency list and the integrate array, it should also start with node 1, not 0. So I'm gonna plus a 1 because I will not use this node 0. Yeah. Now let's just check all the sequences. In the study's example, the sequences may be just with 2 numbers. Actually, the sequence is not just 2 numbers, and you can check it from here because the sequence is 10 to the power of 4. Yeah, it means it is not 2 numbers. So we should be careful about it. So this means we have to read the constraints carefully. Now I'm going to check one item inside the sequence. Basically, this item is going to be an array. So inside the sequence, yeah. So inside the sequence, and then I'm going to check this item as an array. I'm not sure if you are familiar with this kind of for two numbers, I'm gonna put it inside pairwise. Yeah. So if you are familiar with it, it is okay. If you are not familiar with it, basically this pairwise is just pairwise the number together. For example, we have an array 1, 2, 3. So for pairwise, we can get 1, 2 as a tuple, 2, 3 as a tuple. Yeah. So in this way, we have the two edges, one directed to 2, 2 directed to 3. Yeah, because this is why we're going to use the pairwise. Basically, we are building the graph. Yeah. So for AB inside of the pairwise with this item, maybe I'm going to use an array. Maybe it is better. Yeah. So for AB inside of the pairwise of the array, I'm going to build a graph. So it means A directed to B. So basically, GA should append B. Yeah. And then for the degree of B, so the integrate for the integrate of B should plus equal to 1, because A pointed to B, A directed to B, and B should plus 1 for the integrate. Yeah, currently it is okay. Now I'm gonna prepare a queue and a possible result array. So the queue gonna be the queue, and I'm gonna check all the node, which is equal to which is the integrate of the node gonna be equal to 0. So for I, they in enumerate with the integrate, and I'm gonna check if they equal to 0. Yeah. But I have to be careful. I have to be careful about that, because I didn't use the index 0. But at this position, there is a 0. Yeah, definitely I will put this 0 node inside my queue, but I don't want to put it inside. So how can I do? I can check it from here, or I can do it from here. Maybe I want to do from here. If V equal to 0 and I not equal to 0. So this means I will not consider that first 0 node. This is the index 0. Yeah, because our node is just from 1 to n. It is not included with this 0. So from here, I will exclude that kind of 0. And for the result, I'm gonna prepare an empty array currently. So now I'm gonna start the BFS. So while queue, I will check the length of the queue. So while the length of the queue is more than 1, it means there are 2 nodes. It means I connected with 2 nodes. Definitely, it is not possible. If I connected, yeah, I'm sorry. It is not I connected with 2 nodes. It means I have 2 nodes inside the queue. If I put 2 nodes, so for example 0 and 2, 1 and 2, for example with node 1 and 2, if I put 2 nodes inside the queue, this is not okay, because this means I have 2 possible ways, but I need to only have 1 way. So if the queue is more than 1, definitely it is going to be a false. Otherwise, I will get the node. It equal to the q dot pop left. I pop it from the left side of the queue, and I'm gonna check the neighbors. And then I'm gonna check the integrate. If the integrate for this neighbor, I'm gonna equal to 0. I'm gonna equal to 1 minus 1 first. Yeah, because I checked this neighbor. This neighbor will be disconnected, and I need to minus 1, and I need a check. If this neighbor equal to 0, I want to put it inside the queue. So I want to put this neighbor inside. Yeah. So currently this is the basic structure, but we didn't put anything inside the result array. It is easy. We just need to put the node inside of the result array. Yeah. And where is the node? Node is popped out from the queue, so we need to put it here. Yeah. Now we have the result array and we have the nums. We just need to compare with the result array and the nums. We're gonna return result equal to nums. Yeah. But from here, if there is while check for this queue. If the length of the queue is more than 1, definitely we're going to return false. If everything's okay, we're going to get a result array. And finally, the result array going to compare with nums, because sometimes maybe we only get a number. In this case, we only get a number of 1 and 2, but our nums is 1, 2, 3. Definitely, it's going to be a false. Yeah. But if the nums is only 1, 2, definitely we're going to return true. So this is going to be the entire code for this problem. Now let me just run it to check. Neighbor. For neighbor inside G neighbor, I always made the typo mistake. So it should be inside G node. Yeah, because this is our node. Now, as you can see, it works. Now let me submit it to prove it can pass all testing cases. As you can see, it passed all testing cases, and the time complexity is O m plus n. M is the number of edges, n is the number of vertices. Yeah, let's just check. So n is the nums length, and the sequence's length is 10 to the power of 4, and the sum of the sequence's length is 10 to the power of 5. This is very important. So this means how many edges do we have? 10 to the power of 5. And how many vertices do we have? 10 to the power of 4. So 10 to the power of 4 plus 10 to the power of 5. So basically, the time complexity is nearly to 10 to the power of 5. This is why it is so fast. So we're going to say the time complexity is going to be OE plus V. E is the number of edges, V is the number of vertices. Thank you for watching. See you next time.